So in last night's video, we looked at solving exponential equations that have variables as exponents. And in tonight's video, we're going to be looking at solving logarithmic equations, where we have variables inside of a logarithm. So here we have log base 3 of the quantity x minus 5 is equal to 2. And this type of equation is actually fairly easy to solve if we just take this logarithmic equation and turn it into an exponential equation. So we write this as 3 to the second power is equal to x minus 5, which means 9 is equal to x minus 5, which means that x is equal to 14. Now, for these, it's going to be pretty important that we actually do go back and check our solutions, because there are some numbers we can't take the logarithm of. We can't take the logarithm of 0 or any negative number. But in this case, we check, and we plug in 14 for x. We get log base 3 of 14 minus 5. Well, that's going to be equal to log base 3 of 9, which is 2, which is exactly what we found it should be, so we're in good shape. So let's take a look at another equation. So here we have another logarithmic equation. This one's a little bit more complicated because there are two logarithms in it. Fortunately for us, we do notice that both of the bases are the same, and the other fortunate thing is that the equation is equal to 0. So for this one, the first step I can take is I can actually add log base 5 of the quantity 2x plus 1 to each side. So when we do that, we're in this really great situation where we've got one logarithm base 5 is equal to another logarithm base 5. And in this case, it must in fact be true that these two insides, what we're taking the logarithm of, must be equal. So what that means for us is that 7x minus 3 is equal to 2x plus 1, which means that 5x is equal to 4, which means that x is equal to 4/5. Checking here is a little bit more difficult. We'll go back to the original equation. We'll get log base 5 of 7 times 4/5 minus 3 minus log base 5 of 2 times 4/5 plus 1. And what we're going to end up when we deal with our fractions in here is we're going to end up with log base 5 of 13/5 minus log base 5 of 13/5, which very fortunately is equal to 0. So that all worked out pretty well for us. So here we have another one. There are actually a couple ways that we could approach this. I'm going to solve this in two different ways. The first is I could use my power property of logarithms, and this equation becomes then 2 times log base 4 of x is equal to 7. So log base 4 of x is equal to 7/2. Rewriting this as an exponential, we get that 4 to the 7/2 power is equal to x. And 4 to the 7/2 power, that's, well, so we'll take the square root of 4 and get 2. 2 to the 7th is 128. So x is equal to 128. Another way we could do this is we could go directly to writing this as a logarithm. From the beginning, we could go directly to writing it as a logarithm, and we'd get then that 4 to the 7th is going to be equal to x squared. And then we can square root both sides to get x by itself, and we would get that x is equal to 4 to the 7/2, which is 128. And again, you should check your answer, but for the sake of time in this video, I'm not going to do that. But you should be checking every answer to every logarithmic equation that you solve. So here this one's kind of nasty. At least the two logarithms have the same base. Remember, when there's no base written there, the base is 10. The one thing that makes this one not quite as nice as a previous similar example is the equation's equal to 1 instead of 0. So what we'll actually need to do here is we'll need to use our product property of logarithms. So doing that, on the left-hand side, we can get log of x times x plus 9 is equal to 1. So log of x squared plus 9x is equal to 1. And then we're going to need to go ahead and write this as an exponential equation. So I'll just put this little 10 here, so remember we're dealing with log base 10. So 10 to the first will be equal to x squared plus 9x, which means that x squared plus 9x minus 10 is equal to 0, and I can factor into x plus 10 and x minus 1, which means that x is equal to negative 10 or x is equal to 1. Now we're going to go back and check. So checking with x equals 1 back up here, we'll get, okay, log of 1 plus log of 10. And log of 1 is, well, 10 to the 0 power is 1, so that's just 0. So this is just going to be equal to 1, which is what we wanted it to be equal to. So this does, in fact, work. And we don't need to go very far checking this. We plug this back in, and when we start writing log of negative 10, and we recall that 10, we're never going to be able to raise that to any power to get, we're never going to be able to raise 10 to any power to get negative 10. This doesn't work, so our solution is x is equal to 1, and that's exactly the reason that we go back and we check our solutions. So here are 3 problems I would like you to prepare for class tomorrow. I will give you a little bit of guidance, which is to remind you that in both of these instances, you can use the power property of logarithms backwards from how we've done it before. So in this case, the 3 could come up as an exponent for the x here. Similar idea in problem number 2. That's going to help you apply one of the techniques you've learned earlier in the video. For both of these problems, please make sure that you check your answers. I will be looking for that when I grade this assignment. This problem is just like what we had in the previous night's homework, and you do not need to check your answers to this one. I'll see you tomorrow.